areas, including concentration phenomena, log concave densities, non-asymptotic and asymptotic random matrix theory, and so on. So it's a great pleasure to have him. So he'll be giving 2 lectures on functional inequalities and moment estimates. So let me just remind you that one is that the slides are already there on the usual place. So it will be sent in the chat also, the link. So you can view it as you listen to the lecture. Second is if you have any questions, you can ask them in chat. And if needed, we will interrupt the speaker. Okay, please go ahead.
Thank you very much. Thank you very much for the invitation. And I will speak about, as already mentioned, about functional inequalities and moment estimates with applications to concentration of measure. And okay, let me perhaps stop the video. Okay. And I was informed that there were going to be some students in the audience, and it would be good to also introduce some background and classical results. So this is how I will start. And then I will, so I will start by describing concentration for Lipschitz functions, starting with the Gaussian setting, and then I will move on to non-Lipschitz functions. My goal is to show how concentration for non-Lipschitz functions can be obtained from moment estimates and how those moment estimates can be derived from functional inequalities. So since it's an online presentation with slides, I will not present detailed proofs, but rather I will give an overview of results that have been obtained in the last, I would say, 30 years. So let's start. Okay, so I would like to start with something very classical, the Gaussian concentration inequality. So it's a very well-known and fundamental result that was obtained in the 70s, independently by Borel and Sudakov-Tsirelson. So its formulation is very easy. If we have a standard Gaussian vector in Rn, so a Gaussian vector with independent components, Gaussian components of mean 0 variance 1, then for every Lipschitz function, say L Lipschitz, we have the following tail estimate, or an estimate on how much it can deviate from its expectation. So we have a sub-Gaussian bound here. And what is important is that it is dimension independent. So if we increase dimension, the bound for fixed L remains the same. So the original formulation was slightly different. We had median here, slightly different constants, but both versions, concentration around median and around expectation, are equivalent. And both are called the Gaussian concentration inequality. Okay, and of course, like most of you for sure know, it has proved very useful in not only in analysis of Gaussian processes, but also in geometry, for example, where it replaced the isoperimetric inequality on the sphere and allowed for many probabilistic tools. So the original proof was based on this isoperimetric inequality on the sphere, and it was somehow projected. Projection from the sphere to Rn gave the Gaussian measure asymptotically. Okay, one more remark. If f is just a linear functional, then f of g is a one-dimensional Gaussian variable, so we know very well how the tail behaves. And from this, it follows that this right-hand side is optimal in the sense that this constant 2 here is optimal. Okay, I want to speak about functional inequalities, and the most important one for me will be the Luxiable inequality, which was introduced, well, I think first by Federbusch and then by Gross, but it's usually associated in this form that I'm going to present it. I think it was introduced by Gross also in the 70s. So we will say well, for the first part of my talk, I will speak only about Rn and the usual gradients. So we will say that a measure, probability measure mu on Rn satisfies this Luxiable inequality with constant k if the entropy of any smooth function squared is bounded by the second moment of the gradient. And I should probably explain here, we will deal with probability measures almost only. So I will use this notation. I will just treat functions on Rn quite often as random variables. But okay, we also have a formulation in terms of a vector, random vector on Rn, and well, it is just a translation from this distribution formulation. So by an entropy, which appears here, I mean the following expression. So what is important is that it is of the form expectation of phi of g minus phi of expectation of g, and of course the same for random variables here. And phi is a convex function, right? Here it's x log x. We will see other functions as well later on. So in particular, we know by Jensen's inequality that it is non-negative. And one important aspect of this inequality I would like to mention now is that it tensorizes. If we have two measures that satisfy it, then also the product measure satisfies it. Okay. So I have 2k here. This 2 is just to be able to say that the standard Gaussian measure satisfies this inequality with k equal to 1. So this is the result by Gross, 1975. And let me just very quickly mention the original proof, which can be a rather involved but instructive exercise for students. So Gross first established a discrete inequality on a 2-point space, -1, 1, where both values have equal probabilities 1/2. Then, since this inequality he obtained also tensorizes, he passed to the product, and now having independent random variables, like symmetric ±1 random variables, he used CLT to pass to the Gaussian measure with some Taylor expansions and relatively simple estimates. Like this discrete inequality was probably the most involved part once we know that the inequality tensorizes. But now there are many different proofs. Michel Ledoux mentioned in one of his talks that he could count 15 various proofs. There are analytic proofs, semi-group methods by stochastic calculus. One proof which gives many examples, it's a very important result from the 80s, is by Bakri-Emery, and it tells us that if we have a measure whose Hessian, this is how I will denote the matrix of second-order derivatives, is bounded from below in the semi-definite order for some k greater than 0, then it satisfies the Luxiable inequality with constant k, so it agrees with this Gaussian measure. And what is the connection with concentration? We have a theorem. It was, I think, it first appeared in a letter from Herbst to Gross, and I don't know when it was published for the first time, but it's a very important theorem in the theory of concentration of measure. If a random vector satisfies the Luxiable inequality with constant k, then we have the following tail bound. So here I wrote it in a one-sided version, right? When we, of course, we can add absolute values here and get 2 here, and k equals to 1 for the Gaussian measure. So together with the result by Gross, it recovers the Gaussian concentration inequality. So let me clear the drawings. And let me show this argument. This is one of the few proofs that I would like to show, this one for the sake of the students. So we apply the Luxiable of inequality, maybe let me show it again. We apply it not to the function f, but to the function e to lambda f over 2. So we had entropy on the of the squared function on the left-hand side. So this is just the entropy. And here, when we differentiate e to lambda f over 2, we had 2, we have the square, so we have this constant 1/2. We have, this is just an application of this Luxiable of inequality. And now if the function is Lipschitz, then this guy is pointwise bounded by L squared. So we are left with the expectation of this exponent here. And well, once we move certain things to the left-hand side, we get such an expression. This is ugly looking, but well, I don't have time to get into details. It's again an exercise. When you look at it for a while, you will see that this is the derivative of such a function. And now, since this function converges as lambda goes to 0 to the expectation, for example, by the L'Hopital rule, then we can just integrate it out. And after some algebra, we get a bound on the log Laplace transform of the centered random variable. And now we do the usual thing. We use the Chebyshev's inequality. So by the exponential Chebyshev inequality optimized in lambda greater than 0, we get such an expression. I think you have to plug in t over kl squared as lambda, and then you get the result. So as you can see, it's a very soft and clear argument. So this recovers this Gaussian concentration equality for Lipschitz functions. I would like to speak about non-Lipschitz functions. So let's look at possibly arguably the simplest non-Lipschitz functions. Let's look, well, we want it to be in a high dimension because we are interested in concentration, which is a high dimensional phenomenon. So let's look at a quadratic form. Probably the simplest non-Lipschitz function would be to square just a one-dimensional random variable. Here we have the a quadratic form. We can assume that it's given by a symmetric matrix, and I will denote by this skew brackets. I will denote the standard inner product on Rn. So this is our expression. GIs are independent. And this variable can be analyzed rather easily because, well, if we write that A is U transpose du for some orthogonal matrix U, then we can write this as A UG, sorry, not A, but now D. UG, and now this guy has the same distribution as G because G is rotationally invariant, right? So, and D, let's say that D is diagonal with eigenvalues lambda I. So in fact, after this change of basis, we see that our quadratic form is a sum, well, a linear combination of squares of independent Gaussian variables. So sums of independent random variables are classical. There are many inequalities, and one of them, well, a particular version of Bernstein's inequality tells us how to handle such linear combinations. What is important is that, well, the square of a Gaussian random variable behaves more or less from the point of view of tails like an exponential variable. The tail decay here is exponential, and that's why we can apply this Bernstein's inequality and obtain such a bound. So now, since we square the Gaussian variable, we cannot have the sub-Gaussian behavior for the whole range of t. But it turns out that we have somehow two ranges. First, for relatively small t, we have a sub-Gaussian behavior, which can be expected from the central limit theorem. And then in the range when the central limit phenomena do not apply, we have an exponent, do not apply at the level of tails, right? We exponential tails. We have this behavior. What is important is, of course, that this parameter is smaller than this one. And now when we go back to our original formulation, to the matrix, we see that the sum of the eigenvalues is just the Hilbert-Schmidt norm squared, the squares of eigenvalues, and this is the operator norm of the matrix, right? So just to fix the notation, by Hilbert-Schmidt norm, of course, I mean the sum of squares. And oh, sorry, I should explain now. I will leave it here like that, but I will try to write norms on Rn or on spaces of matrices with single bars, because later we will have moments and I don't want to confuse them. So with double bars, I will denote norms of random variables, and with single bars, norms on Rn or on the space of matrices. So it's this behavior. And let me mention one thing here, which is different in this formulation in terms of matrices than in the formulation for sums of independent random variables. So in most inequalities for independent random variables, when you look at tail decays of or moments, the estimates are monotone in terms of the coefficients, right? If you increase the coefficients, then the tail becomes worse. Now here, if we look in terms of the quadratic form and those coefficients, well, the Hilbert-Schmidt norm is also monotone. If you increase the coefficients, it increases, but it's no longer true for the operator norm. So it's not one unconditional, right? It may happen that we even set some coefficients to 0 and the bound on the tail becomes worse. So it shows that even such quadratic form exhibits a much more complex behavior because the cancellations are more tricky, right? We don't have this monotonicity as for sums of independent random variables. Okay. And this inequality is usually referred to as the Hanson-Wright inequality. Actually, Hanson and Wright proved in the 70s something slightly different. They had something slightly different here, operator norm, but of a different matrix. At the same time, they had a more general setting. And then even if the coefficients are from a Banach space and the vector is Gaussian, this was recovered many, many times by many authors. What is important is that for the Gaussian setting, this inequality, this upper bound on the deviation probability can be reversed. So we have also estimates from below up to constants. And I should mention from this point on, whenever I write capital C or little c, I will mean a universal constant which does not depend on any other parameters. And for most of the time, I will not be concerned with the constant. So in this Gaussian setting for the concentration inequality, I wrote precise constants, and from now on, I will not care about them. So a few remarks. There are counterparts already in this work by Hanson and Wright for independent random variables with sub-Gaussian tails. So here I mean that we have a quadratic form in such independent random variables, and the bound is the same. They should be centered. I didn't write it. It can be derived also for random vectors which satisfy this concentration property for Lipschitz functions as the Gaussian ones, but it's even enough to have convex Lipschitz functions. And I'm just mentioning it because in a moment I will prove this inequality using the Luxiable inequality, but I want to stress that this is just for illustration because it can be obtained under weaker assumptions. But how can we prove this starting from the Luxiable inequality? So we are going to use, well, you can do it in many ways, but I want to use moments. So Aida and Stroock in 1994 obtained the following moment inequality. This is the first moment inequality in this talk, valid under the Luxiable inequality. So now for all smooth functions, the rth moment for r greater than 2 of f of x, which satisfies this Luxiable inequality, is bounded by the rth moment of the gradient. So here by this I mean, of course, the rth moment of the Euclidean norm of the gradient multiplied by square root of 2kr. So what is important here is that the behavior in R is this square root. And in the Gaussian case, this was obtained earlier up to constants in the 80s by Moret and Pizier. And this is also a version of the Herbst argument. I won't present the proof, you just differentiate this function, which you can see here in R. And again, some entropy of certain function will appear, which you can estimate by the Luxiable inequality. You will get some cancellations, and in the end, you can just integrate. So this is rather elementary. Let me mention, I will come back to it in the second part, that Aida and Stroock proved it in a much more general setting than Rn. And let me also mention another inequality of this type. So the Poincare inequality, which is another inequality important, right? Not only in PDEs, but also here in probability. Poincare inequality also implies a moment estimate of a similar form, but now the growth here is exponential. This is a linear growth of the moment in R. It will correspond to sub-exponential decay of the tail. So I mention it because the Luxiable inequality implies the Poincare inequality. It is known that the Poincare inequality implies exponential decay of the tail, and I want to argue that there are at least two functional inequalities. We will see others, but at least two at this moment, which imply some growth of moments, estimates on growth of moments with various powers of R. Okay, so here I repeat the estimate by Aida and Stroock. And now, by Chebyshev's inequality in L-R, we very easily get this bound. So now, well, let's see, if our function is Lipschitz, then this gradient is bounded by L, by the Lipschitz constant. So the only dependence on R is this square root. So if we plug it here and reverse to have t here, right, roughly speaking, t must be equal to square root of R, we will get e to minus t squared for the deviation. So up to constants, we recover this Gaussian concentration inequality, but in the proof of the Herbst argument, I mean, in the Herbst argument, in the proof of the deviation Gaussian concentration inequality, at some point we needed for this differential approach to work to estimate the gradient pointwise by the Lipschitz constant. Now in this formulation, if we have some other bounds on the gradient, for example, we know that it grows quadratically or with the norm of x or some other bounds, which allow us to estimate the moment of gradients, for example, to this form, then we will get a similar estimate here, but with a different power of R. And again, plugging it into Chebyshev's inequality and reversing will give such a bound. So we can see that we can go beyond this sub-Gaussian tail decay, and we know from this quadratic form example that, well, we may be forced to do it. However, for the quadratic form, we will get an exponential behavior here with the some Lipschitz constant here. Sorry, not Lipschitz constant, but the Hilbert-Schmidt norm here, which is not the Hanson-Wright inequality, which was the precise tail estimate. So now I would like to show how this inequality can imply the Hanson-Wright inequality. And the general rule, by using this Chebyshev inequality, is as follows. If we have a bound of moments of the form A times R to beta, then it translates into a tail estimate T over A to 1 over beta. And as in this Hanson-Wright inequality, we had two ranges, a sub-Gaussian one and sub-exponential one. So it corresponds up to constants at the level of moments to a bound like that. So it would be square root of R times the Hilbert-Schmidt norm plus B would be the operator norm times R. So this is the correspondence. In one way, this is just the Chebyshev inequality. In the other direction, you can integrate by parts to go from tails to moments. Okay, so this is a simple bound that you can obtain from the Luxiable inequality. I believe it might have been a part of folklore, but we wrote it with Witek Bednosz and Paweł Wolf a few years ago. So I don't assume here the Luxiable inequality. I assumed the consequence of the Luxiable inequality due to Aida and Stroock. Right? So the K here is not the same K as we had in the Luxiable inequality, but okay. If we start with such moment estimates valid from all R greater than 2, then we have, oh, and here I apologize, this should be R. I was having different notation in different papers. I was trying to change all P's to R because we will use P for something else later, but I missed this one. So for any function of class C2, we have the following estimate. We have the rth moment, it's smaller than square root of R times the first moment, and now I wrote 2 here to stress that it is the Euclidean norm of the gradient, plus R times the operator norm of the Hessian of F. And well, this Hessian is random here, right? It's evaluated at X, so we need to take the rth moment. And this inequality is very easy. You just apply first this bound, and then you apply it again together with the triangle inequality to the Euclidean norm of the gradient. And when you, okay, the Euclidean norm of the gradient is not a smooth function, so you need to have some smoothing, but basically the operator norm of the Hessian is like the local Lipschitz constant of the Euclidean norm of the gradient. So just by an application and iteration of this assumption, you will get this bound. And now if you replace, so it's all very elementary. If you replace this first moment of the gradient with the second moment of the gradient, and use our assumptions, but just for R equal to 2, you will, and the triangle inequality, you will get this part. So I don't have time to go into details, but this is all very elementary. So you see this square root of 2 here comes from R equal to 2 in our assumption. And as a consequence, if we go to the tail estimate and assume that the Hessian, the operator norm, is bounded by L, then we will get such a bound. And what is important here is that this, oh, here, another typo, sorry, there should be no new here. What is important here is that the gradient is averaged. It's averaged inside the norm. This allows us to recover what we want. So this is the bound. And now when we look at such a function, and assume for simplicity here that our random vector is of mean 0 and covariance matrix equal to identity, like the Gaussian vector, standard Gaussian vector, then we see that the expectation of the gradient is 0. So this part vanishes. And the Hessian is our matrix of coefficients, roughly speaking. So we will get such a bound. K is a constant now, right? Because it's not exactly the K from the Luxiable inequality, but it's comparable to it. And K in the Luxiable inequality was 1. So this is how you can derive this this estimate for quadratic forms from the Luxiable inequality. It's one of the possibilities. But, well, one can argue that the quadratic form is a very simple non-Lipschitz function. And I also mentioned that the tail bounds, this Hanson-Wright tail bounds of this Gaussian exponential type, that they can be derived under weaker assumptions. So let's think still about polynomials, but of higher order. And, well, I would like to describe a very nice result due to Latała. But, well, while the result is very nice, the notation is not. So I apologize for that. Now, this is the part where we will encounter the most involved, I would say, piece of notation in my talk. As we will see, this is the fact of life. The quantities that I will show you do appear in moment and tail estimates. So I want to focus on multilinear forms of higher order. Another typo. This should be I. Not sorry about that. I and not 1. So we have D-indexed matrix or a tensor, if you prefer, which will define the multilinear form. And we have D-independent standard Gaussian vectors. So all our doubly indexed variables gi, n gik are independent standard Gaussians. And, well, I will not use this notation too much, but just at the beginning, no, sorry, I will use this notation in a few slides. When we have vectors in Rn, by their tensor, I will mean a matrix in which, well, a D-indexed matrix at position I1 up to ID, we have just the coefficient I1 from the first vector multiplied by coefficient I2 from the second vector, and so on. So we have this notation, and another notation I will use when we have the inner product on matrices or multi-index matrices. So, oh, sorry, A times B. This is like the Hilbert-Schmidt inner product. A times B is just will be the sum A1 up to AD, A1 AD, B1 BT. This is just to have a short notation, right? So this is the form of order D defined by our matrix of coefficient evaluated on this vector G, and this is the D-linear form. And I will be interested in both quantities under some assumptions on the matrix A. If it is symmetric and vanishes on diagonals, the tail behavior of these two random variables is comparable up to constants. This is a quite well-known fact known as decoupling. So I will work mostly with this one, but this one is in some sense more natural. Working with this one is easier because if we condition on, let's say, the first D-1 vectors, then we will get a sum of independent random variables conditionally on the first D-1 vectors, and we can apply known inequalities. Okay, so for the quadratic form, the tail behavior was governed by two quantities, the Hilbert-Schmidt norm and the operator norm. And now we will have more of them. And it turns out that they will be indexed by the family of partitions of the set 1 up to d, where d is the degree of our polynomial, into non-empty pairwise disjoint sets. So for such a partition consisting of sets I1 up to ik, we define a norm of the matrix A, and I will show you the formula, but I will not let you watch it for too long. I will pass to the examples because I believe that it's impossible to read this formula during the talk. It's the notation, well, as I mentioned, is quite ugly here. So this is the formula. Let me just say that philosophically, what is going on here is that when you have a matrix like that with the indices, you can group these indices. Group these indices according to the partition. So when we group it into k groups, we can think of our matrix as a matrix with k indices, and then it defines a multilinear form of degree k. And we look at the norm of this multilinear norm. So these norms are, one could say in functional analytic terms, injective tensor product norms of A seen as a multilinear form in all the possible ways. But such an interpretation doesn't help much. Let me show you examples. And we should, let me just move. Oh, sorry, I think I muted myself by accident. Let me clear this. Okay, let's look at a matrix of order 2, and let's look from the right-hand side to the left-hand side. So in the Hanson-Wright inequality, we had the Hilbert-Schmidt norm. The Hilbert-Schmidt norm is defined like this. Using the Cauchy-Schwarz inequality, you can write it as by duality, right? As such an expression. So we have a test matrix, which should itself have the Hilbert-Schmidt norm bounded by 1, and we evaluate it, right? On we take the product with our matrix A. So we have one test vector, and this test vector is indexed by ij, which corresponds to the first index I and the second index j. So the operator norm, which was another norm appearing in the estimate, can be written by duality in this form. So we have now two test vectors. Each of them is indexed by just one index. It's xi, yj. Both of them should have their Euclidean lengths bounded by 1. And we plug them into A seen as a two-linear form. So this is our operator norm. And since we have two vectors, we have this notation corresponding to the indices. So now what happens, I guess everyone can see what will happen in higher degree. If we have 3 degrees and a partition of this form, 1 and 2 go together, 3 goes separately, then we have 2 elements of the partition, so we will have 2 test vectors, but one of them will be indexed, doubly indexed, xij, the other one will be indexed just by 1 index k, and the same constraints we have here. So of course, using duality, you can, for example, write it in this form, supremum square root, let's say, over ij, sum over k, aij k xk squared, right? Where, well, I should write yk here, perhaps sum yk squared is smaller than 1. I just use the Cauchy-Schwarz inequality for x to get rid of x. Or you can get rid of y and switch the external and interior sum here, but in general, you can get rid only of one of those indices. And the operator, the norm corresponding to the partition into a singleton will have again one test vector, triply indexed. So it will be aijk xijk. So it will give you again the square root of the sum of the squares of the coefficients. So whenever we have the trivial partition into a single set, then it is a counterpart of the Hilbert-Schmidt norm. And this is the only of these norms that is monotone with respect to the coefficients. Maybe for completeness, I should write, of course, we also have ijk 1, 2, 3, and it will be a supremum ijk, aijk, xi, yjzk. And the constraints are the same. The sums of squares should be at most 1. And so I hope that this notation is clear now. And there is a result by Latawa, which generalizes this Gaussian case of the Hanson-Wright inequality. So it turns out that if you want to estimate the norm, that Arf moment of such a D-linear form in independent Gaussian vectors, then we will have to take into account all the possible partition norms, those injective tensor product norms that I described, and add them up with various powers of R. The power of R depends on the cardinality of the partition. So, for example, in the quadratic form, we will have two partitions, one corresponding to operator norm with power R to the power 1 here, because operator norm is a partition, corresponds to a partition into two sets, and the Hilbert-Schmidt norm, which will have square root of R here. And it is a two-sided estimates with constants now depending only on D. And as a consequence, we'll get such a tail bound from above and from below. So you can see this is what I said before, that this notation may be ugly, or the inequalities are not very pleasant, but they are two-sided. So there is not much we can do about it. This is how such polynomials behave. And due to this decoupling I mentioned before, if we assume that A is symmetric and vanishes on all the diagonals, then also for this form with a single vector, we have the same here. So let me show you what it, well, I have like a minute and a half, maybe. Let me show you an example, and we can make a break. So if we have a symmetric random variable, sorry, a symmetric matrix, and we have a form of order 3, then we have the following estimate up to constants for moments, and I assumed it's symmetric because then we have only 3 partitions, right? If we partitions into two sets in a different way, then it will give us the same norm. So we have such a behavior, and we have now the tail behavior, which has 3 regimes. Again, we have the Gaussian behavior for small t. We have the sub-exponential behavior, and we have even weaker tail decay for large values of t. This is two-sided, and let me mention that it's always the case that the norm corresponding to the largest, to the trivial partition, this is the largest one. So calculating these norms is not as straightforward, right, as calculating this, because this is just the square root of the sum of squares of the coefficients. So if you don't care about precise tail behavior, but you're interested only behavior at infinity, you can always replace all of them by this norm, and you will get t over this norm to the power 2 over 3. So this recovers then up to constants classical estimates for such forms due to Nelson and Bonamy from the 70s. Okay, and I guess I should stop here because it's been 45 minutes. So later on, I will show you how to combine this inequality with functional inequalities to get some concentration results beyond those bilinear forms. But now let's make a break.
Okay. Any questions? There's a lot of time for asking questions.
I have one thing to clarify.
Yes, yes.
So when you put this norm R, do you take the expectation to the power R and then again a 1 over R, or no?
Yes, yes. Oh, sorry, I should have explained this. Of course, yes. This is what I mean by
Okay.
XR. And going back, right. So this is exactly why I could refer at some point to Chebyshev's inequality here, right? Because here, like, this guy will be bounded by expectation of x to the power r divided by exr to the power r, and we will get a cancellation. What survives is just e to minus r. Right. So this was the idea. Okay, maybe let me.
Any other questions? Okay, so if not, we will again resume at 3:30, which is 12 minutes from now.
Okay, so thank you. I will mute myself for the moment and check on my daughter.
Okay.
Yeah, if anybody joined late, again, the slides are available on the website. recording.
Maybe.
Okay, so can I continue now?
Yeah, please.
Okay, thank you. So we finished with a result by Rafał Latała, which tells us how to estimate from above and from below by the same expression up to constants multilinear forms in independent standard Gaussian variables. And now I will have also quite ugly looking proposition which allows to transfer such inequalities to more general functions and measures. And this is from my paper with Paweł Wolf. And well, the formulas are not very pleasant, so let me guide you through them. So we have a random vector on Rn which satisfies such a bound. And well, I put here gamma to show that it's more general than just the sub-Gaussian behavior. So you may remember under the Luxiable of inequality, we have gamma equal to 1/2. Under Poincare inequality, for instance, we have gamma equal to 1. Right, so here we have an arbitrary gamma, and we will need IID standard Gaussian vectors independent of x. So this is assumed for, let's say, C1 functions, right? Then if we have a function which has d derivatives, we have the following expression, and it gets more and more complicated with capital D. What do we have here? We have the moment of the Hessian of f acting on those vectors g1 up to gd. So the first expression here, the Hessian is a capital D indexed matrix, so we may treat it as a D-linear form, and we evaluate it on those random vectors independent of x. But, well, it still depends on x, right? So we may say that the moment is taken collectively with respect to x and gi's. And then we have sums from 1 to d minus 1 of similar expressions with different powers. But here we already have this matrix of derivatives of order d integrated, right? So x gets integrated out, and these are moments calculated just with respect to gi's. So here, after averaging, we will get a matrix with little d indices. We apply it as a multilinear form to our vectors, and we calculate the moments. So it's similar to what we have seen in when we were deriving the Hanson-Wright inequality. The gradient there, just for d equal to 1, little d, was also integrated. Okay, let me show you, just to convince you that it's very, very easy. Let me show you the proof, or the beginning of the proof. This is just induction. For the main observation is that, well, when you evaluate g, or you treat, okay, take the inner product of g and another vector, you will get just a one-dimensional random variable of variance given by the Euclidean length of x squared. So we know how the moments behave. From above and from below, we can estimate them by square root of r times x times some constant. So the previous result for capital D equal to 1, it is just rewriting this inequality using Fubini theorem. This is just a very easy, but a very easy observation, which is in fact the only observation for this proof. So when you raised everything to power r, this is our assumption, right? Our assumption was that the moments were bounded by the moments of the gradient. So here is the moment of the gradient, and this Euclidean norm is replaced for fixed x, so conditionally on x, by the moment with respect to g of this gradient, inner product with g. And to do it, since we have square root of r here, we need to steal this square root of r from r here from the prefactor. Right, so this is very easy. And then it is just induction. We apply the case d equal to 1 to get such a bound. And now instead of g, I write the first of my independent Gaussian vectors. Now I just used the triangle inequality in LR, subtracting this expectation. Here I wrote this expectation with respect to x outside. Here I wrote it inside, but it's all linear, right? So it doesn't matter. I mean, we have independence of x and g. The second summand here is the summand that appeared in our estimate. So we just need to take care of this one. And to this one, we again apply the case d equal to 1, but conditionally on g1. So we apply it to such a function. g1 is fixed at the moment. And we just used the definition of the second derivative, right? That differentiating such a function in direction g2 is given by this formula. And this is the end of this proposition. As you can see, for higher d, it goes in the same way. So this is very easy. But what is the advantage of this? Here you can see we have moments of some Gaussian multilinear forms. And here you can say that it's a moment of a random Gaussian multilinear form because x here makes the coefficients random. But for those moments, we have our estimate by Latała. And now we can apply it here directly and here conditionally on x. And we get such a theorem. Here I specialized to the case coming from the Luxiable inequality and not to the general case. If we assume that x satisfies the Luxiable inequality, then we have such an upper bound on moments. And I'm not sure now, perhaps I missed some square root in the coefficients, but let's not pay attention to the dependence on k. Let's treat k as fixed. Yes, probably k here should be replaced by square root of k because this is how the k from the Luxiable inequality enters the moment inequality. So I apologize for that. I will not change it now. It's not so important. So the moments are bounded by the moments of this partition norms applied to our matrix of derivatives of order capital D. So here we have to do some integration of powers of derivatives of f. And here we have just those norms evaluated on deterministic matrices. These matrices are deterministic. So now if we assume that if we again pass from moment estimates to tail estimates, and we assume, for example, that our function has uniformly bounded derivatives of order capital D, then we will get such a tail behavior. So you have to take the supremum over x here for little d equal to capital D. For other little d's, you have this gradients or higher order derivatives integrated. So this is important because it tells you that you can get an inequality in which you don't have to assume much about lower order derivatives, right? Just the higher order moments or pointwise bounds on higher order derivatives are needed. But well, let's be honest, already calculating this expected norms is not very pleasant, right? This expected derivatives. And when we want to calculate then those partition norms of them, this is kind of hopeless because please remember, it may happen that you decrease the coefficients and increase the norm. So you cannot estimate here so easily. There are examples in which it is done and those inequalities are applied. Whenever I see such an example, I'm of course very happy. But if you are interested in somewhat weaker bounds, just for larger t, then perhaps it may be a good idea to replace all those norms. The largest one of them is the one corresponding to a partition into a single set, right? And this one can be somehow estimated because this is the Hilbert-Schmidt like norm. Well, anyway, let's focus on polynomials for a moment. Or maybe let me just say that this result can be seen because it was proved by a very soft method, right? Just by induction and the Fubini theorem, whereas the result by Latawa really uses some chaining, difficult technical tools. So this may be seen as a transference principle of those inequalities for polynomials of special form, right, for those multilinear forms in Gaussian vectors, to more general functions for more general measures. Right? But when we specialize to polynomials,
Radek, one question.
Yes, yes.
In the previous, you said that you are assuming the Luxiable, but is it possible that, like in your first talk, you can take the weaker condition on the moment?
Yes, yes, but, yes. This is just for simplicity. If you assume Poincaré, then the powers here will change. You will get a result of the same time, but with different powers. You will not get this sub-Gaussian behavior, but some other behavior, because in the previous inequality, here gamma will be 1 and not 1/2.
Okay.
Okay, so for here we have the supremum over x, but if x is a polynomial of degree capital D, then derivatives of order d are constant. So to simplify it, we can write the inequality in such a way. And here one may remember then for little d equal to capital D, this expectation is actually not necessary because the derivative is constant. And again, sorry about it, I believe that it should be square root of k here, but I will check it and send the updated slides. Okay, in the Gaussian setting, so when k is roughly speaking 1, this inequality for polynomials can be reversed. Again, like in the result by Latawa. So we will get a different constant here and 1 over c instead of this 2. Right? And so this inequality can be obtained for Gaussian polynomials also in a different ways, using this decoupling techniques and infinite divisibility of Gaussian variables and some Hermite polynomials, some Gaussian techniques, and this is how you show that this inequality can be reversed. But such a formulation for general polynomials turns out to be new even in the Gaussian case, right? Because the result by Latawa was for polynomials which only had which were affine in each variable, such tetrahedral polynomials. Such an inequality also can be written for independent sub-Gaussian variables in the same form, but only for polynomials. It is known that just sub-Gaussianity will not give you concentration for general functions. And there are also some generalizations to Banach spaces, coefficients from Banach spaces. I don't want to speak about it. Now, I think to be on time, I need to skip a part. So let me just very briefly, without explaining the details, say about other assumptions on moments. So instead of the Loxabolev inequality, you can have something which is known as the modified Loxabolev inequality, which is written in this form. And psi is a Young function, which is roughly speaking such a function. So convex increasing 0 at 0, possibly taking value infinity. So this area came from the need to find a simple proof of Talagrand's two-level concentration for the exponential measure. And then Bobkov and Ledoux introduced such an inequality. They observed that the exponential measure satisfies the Loxabolev inequality, but if you assume that the partial derivatives are bounded by something smaller than 1, roughly. So this inequality corresponds to x squared for small values of x and infinity for larger values of x. But then it was generalized to such a form of the inequality by Gentil-Guillon-Miquelon, and it allows to give other ranges of concentration. So in some sense, it is also related to the question about weaker integrability conditions. Like if you want a concentration independent of the dimension, then you have to assume at least the Poincaré inequality. But if you want something stronger than exponential but weaker than sub-Gaussian, for example, then these are the inequalities which can give you this. And well, I don't have time to go into details, so let me just tell you one thing, that under certain assumptions on this psi, you can write a tail estimate, but of a different form. I will not define the norm here. The point is that this is what I can say, that for each r, you can have a norm on Rn related to this function psi. I may show the exact definition, but I'm not going to comment on this. It's just some sort of an Orlich norm. And for example, this is square root of r times the Euclidean norm if your function is x squared, like in the usual Loxabolev inequality. But if your function has different behavior, for example, first behaves like x squared and then like x alpha, you have various mixtures of various norms. So by x alpha, I mean the alpha norm on Rn, right? So this is some xi to alpha to 1 over alpha. And you can write it in a very abstract way. So in some sense here, this recovers this result due to Aida Stroock. If you, with square root of r and the Euclidean norm of the gradient under the Loxabolev inequality, but if you have these various types of Loxabolev inequalities, then the dependence on r is hidden in the definition of the norm, because it's not so explicit, right? It's somehow related to this function. And you need some assumptions on this. So let me just show you an example. If you have densities of this form, the behavior will be square root of r times the r norm, r moment of the Euclidean length of the gradient, plus some worse behavior with respect to r, but of the rth moment of some smaller norm. Right, so if alpha is between 1 and 2, then alpha star, this is the Hölder's conjugate, is greater than 2, and then alpha star norms on Rn decrease with alpha. Right? So from this point of view, this expression is smaller. And it allows to give you this type of concentration. So if you have a bound, for example, on the Euclidean, uniform bound on the Euclidean norm of the gradient, and uniform bound on the alpha star norm of the gradient, then you will get such a behavior. And here, you can get other behaviors if you assume that the moments, the gradients are not bounded, but somehow integrable sufficiently well. But then probably this dependence on alpha should not be here. This is probably the artifact of the proof. And let me just show you a question, which is very concrete and which may be very easy, but I don't know, somehow we weren't able to do it. So here I had alpha excluding 1. if our bounds held with constants independent of alpha, then we could get this. So it's a question whether a product of two-sided exponential variables admits such a tail bound. So you look at the Euclidean length of the gradient, and here again, I did not, sorry, it was written in terms of P first, square root of R, and R times the smaller norm, the length, maximum absolute value of a partial derivative. So in such a case, we could do what we did in the Gaussian case and obtain inequalities for general functions, because there are estimates on multilinear forms in exponential random variables. So we could go on with the strategy and obtain a bound for general functions with bounded derivatives of higher order. But this is a question I don't know. Okay, so let me pass to the second part of my talk, and as you can see, I'm a little bit behind my schedule. This will be more probabilistic, at least the setting will be more probabilistic, because we will leave the Euclidean space and we will discuss general measure spaces. So we will assume that we have a probability space with a probability measure mu, and we have a reversible Markov process for which mu is the invariant measure. And then, well, so here I will define briefly the notions that we need, but I will assume that you are familiar with them, because I would have no time to go over it. So L is, of course, the generator of the semigroup on L2. We will work in this L2 theory. This is the corresponding Dirichlet form, and we will assume also, we will consider this Dirichlet form as given by the average of the Carré-Duchamp operator, which is given like that. And for this part of the talk, I will disregard all the questions of domains. So whenever I write some expressions with these generators and other things, I will assume that the arguments are in the corresponding domain. So let me just, to be more concrete, go to some examples. If we have a measure given by some potential V on Rn, then we can represent it under some assumptions on V, represented it as a uniform measure of a Markov process of a diffusion, in fact, with such a generator. For example, in the Gaussian case, the Gaussian measure will correspond to the Ornstein-Uhlenbeck process right here. And then, even though the generator depends on V, it turns out when you calculate this Carré-Duchamp operator that it does not depend on V. So this is the Euclidean, right? This is a function, right? So this is just the Euclidean inner product of gradients. So if you plug in FF, we will have the gradient of F squared, so the name Carré-Duchamp. And the Dirichlet form is the one that we saw in the first part of the talk. If you evaluate it on FF, we will have the second moment of the gradient, right? So this is one example, right? So here a mu, this of FF equals what we saw before. And in full generality, we can, another class of examples we can speak about is given by kernels, which are reversible with respect to our measure mu, which this is the so-called detailed balance condition. And then if we define such a generator, it will correspond to a Markov process, which is reversible with respect to mu. And then the Carré-Duchamp is given by such an expression. So for fixed x, we integrate such an expression with respect to this kernel Right? By kernel, I mean that for each x, this is a measure on our space. Right? And the Dirichlet form is given like this. And now we have two types of inequalities. The first one is the Luxiable inequality, which in our previous setting, for those diffusions, reduces exactly to the logarithmic Sobolev inequality that I mentioned there, except that now we don't have this distinguished Gaussian measure, so instead of 2k, I will write k. It doesn't matter much. And we have a different inequality, a modified Luxiable inequality, which tells us that for positive f, the entropy of f should be bounded by the Dirichlet form evaluated on f and log f. So now, the first one in this generality was introduced by Gross, and it is responsible for hypercontractivity of the semigroup, so increased integrability along the semigroup. This one was introduced rather in the context of Markov processes and convergence to equilibrium. So it is equivalent to some exponential convergence to equilibrium in terms of relative entropy. But I don't want to speak about it now, and I don't have time for this. In the setting of the first half of my talk, they are equivalent with these gradients. Just if you substitute g for f squared and so on, and you use the chain rule to evaluate the gradients, you will see that they translate one into another. But in general, this logarithmic Sobolev inequality is strictly stronger, especially in some discrete cases. It may happen, for example, for the Poisson measure and an appropriate Dirichlet form here, this one does not hold and this one does. So the abstract version of the result by Aida and Stroock. Oh, and now I think I could get rid of this square root of 2 here because I changed the normalization in the Luxiable inequality. The abstract version, in fact, was like that. Like for the Euclidean case, this guy, wait a second, I cannot write, okay. This guy here inside was just the gradient f squared. So they actually proved it in such generality. And now there is a natural question. If one can obtain a similar result under the weaker condition of modified Luxiable inequality, which could be perhaps useful in some discrete, especially discrete situations. And the answer is yes. And in fact, to some extent, some parts of the answer were in the air for quite a few years. So some parts of the answer were presented by Boucheron-Bousquet-Lugosi-Massart in the context of independent random variables. So in 2005, they proved the following very useful inequality for independent random variables. To formulate it, we may forget, we don't need this machinery of Dirichlet forms and things like that. You look at the central moment of f, you have this Gaussian behavior square root of r, and here you have such an expression. You can also get rid of this conditional expectation by some Jensen's inequality. What is important, that you have some sort of a discrete length of gradient. And what is this x I? You simply replace the ith coordinate of the original vector by its independent copy. And this inequality, right? So this is sometimes called Jackknife Estimate, I believe. Such ideas were present before. There was a famous Efron-Stein inequality, which up to constants was this inequality for r equal to 2. So for the variance, it was an estimate on the variance. They generalized it to higher order moments. And it found many applications, also in geometry, but also in statistics and in discrete settings, in combinatorics or computer science. And the point is here that the tools they used, they call them Psi-Sobolev inequalities, but in some other language, they are called Bechner inequalities. So Bechner inequalities, this is not the original formulation by Bechner, and there is a family of Bechner's inequalities which are stronger in general than this one. But for example, for diffusions, the original formulation by Bechner would be the same as the one I wrote. So that's why they are called Bechner's inequalities. They are parameterized by P between 1 and 2. And they are of this form, right, where this E is our Dirichlet form. So please note that this is, again, they are also called Psi-Sobolev inequalities because, again, we have psi of F minus psi of EF, right? And this is sometimes called the psi, sorry, it's phi, not psi, sorry, entropy of F. And here phi is just the power, right? But when you look in the literature at phi-Sobolev inequalities, usually you have a fixed function phi, and you work for this with this fixed function, and you are interested in what consequences this single inequality gives. Here, I denoted the constant by BP because we'll be interested actually in the behavior of those constants when P approaches 1. So in this setting, this is rather called Bechner inequality. So it turns out that for fixed P, when we don't look at the whole range from 1 to 2, but or even just for P separated from 1, this inequality is equivalent to the usual Poincaré inequality, with some constants depending on this P. And those dependence on constants, when you translate one inequality into another, this deteriorates when P goes to 1. But for example, for P equal to 2, you can see that, in fact, this inequality is just the Poincaré inequality, but for positive functions. So it's not difficult to see that it is equivalent to the Poincaré inequality for all functions. Now, if those constants Bp are bounded uniformly when P approaches 1, you can just divide by P minus 1 and pass to the limit and recover this modified Luxiable inequality. And somehow surprisingly, we couldn't find in the literature, we tried really hard, a reverse implication, namely whether the Luxiable inequality, modified Luxiable inequality, implies those Bechner's inequalities with constants bounded uniformly over P. Right? And in many results in the literature, for example, Boucheron-Bousquet-Lugosi-Massart proved first a modified Luxiable inequality in this independent setting, and then proved those Bechner inequalities. This made sense because they got optimal functions in both of them. But there are also quite a few results in which usually it goes like that. First, the Luxiable inequality is proved, modified Luxiable inequality is proved, and then the Bechner inequality is proved with some effort, which is greater than for the modified Luxiable inequalities because the functions are somehow, this function defining entropy has some additional properties. Although, to be honest, quite often one can just modify the proof of the Luxiable inequality to get the proof of Bechner inequality. Anyway, it turns out that when you modified the proof from the independent case, the proved by Boucheron-Bousquet-Lugosi and Massart, and you start with this abstract Bechner inequality, and you assume that the constant, it doesn't have to be uniformly bounded, but you control somehow how it behaves when P approaches 1, then you will get an inequality of this form. And if S equals to 0, so if those constants Bp are bounded uniformly over P, you will get a sub-Gaussian behavior, square root of R, like in this estimate by Aida and Stroock. And the proof, well, it follows really very closely the argument by Boucheron et al. But one needs to somehow adapt it. They worked with concrete expressions which were given by explicit formulas, and we work with generators and some other expressions like the Dirichlet form defined by some limits. So one has to be careful. But the core idea is already in this proof. So now it's a question: what happens if one assumes the modified Luxiable inequality? And we are able to prove that indeed, if the modified Luxiable inequality holds, then the Bechner inequality is satisfied with Bp bounded uniformly by 6k, where k is this constant from the Luxiable inequality. We can prove a little bit more. If we denote by k opt and Bp opt the optimal constants in those inequalities, then we have such a behavior. Moreover, I already mentioned before that for p equal to 2, this Bechner inequality is just the Poincare inequality. And not only the usual Luxiable inequality, but also this modified Luxiable inequality, they both apply the Poincare inequality. And we have, because of this, such inequality not only in the limit when p goes to 1, but also at 2 for optimal constants. So it suggests that probably one can replace this 6 by 2. And if we had some, but we didn't try, in fact, very hard. We couldn't see it. Perhaps it's something that a student can quickly do, or someone younger than me. If we had some monotonicity in P in those inequalities, of the best constants in those inequalities, then we would get this result. But as I said at the beginning, in this talk, I'm not really interested in constants. So maybe I should mention that this constant C here, it is explicit, but I didn't want to torture you with the formulas. Okay, so as a corollary.
Radek, one
yes?
question, sorry. So these are all in the full generality of the abstract space with a semi-Markov chain, not restricted to real.
Yes. This is this abstract formulation. Yes. So for I should mention it for diffusions and this Dirichlet form given by the gradient, when the Luxiable inequality and modified Luxiable inequalities are satisfied, then obtaining this equivalence is easier because then the equivalence of the usual Luxiable inequality and some strengthened Bechner inequalities was known. And on the other hand, the Bechner inequalities I consider here are equivalent to those earlier Bechner inequalities, which is not the case in this abstract or discrete setting. Yes. So in fact, the whole difficulty in the proof here is to take care of the lack of chain rule for the gradient, and that's why one has to work a little bit.
Thanks.
So here, in other words, if the modified Luxiable inequality holds, then we get Bechner, this assumption with S equal to 0, then we have square root here, right? And this is our corollary. And I should also mention that if our Dirichlet form is defined by a kernel, then we can look just at the positive part here and replace this gamma with such a formula. This was in fact the original formulation by Boucheron and co-authors. And it turns out that in many situations, this plus here plays a role, because for some random variables, it may turn out that the upper tail and the lower tail behave differently. And you may want to understand how the upper tail behaves. And if you look at gamma of f, it will not give you the information because it controls also the lower tail. Whereas this gamma plus is fitted for the upper tail. Okay, so I don't have much time. Let me just mention that this can be applied then automatically to many settings. Okay, to be honest, the application always goes like that. Someone earlier worked hard and developed either Bechner's inequalities or modified Luxiable inequalities. And then what we can do is either apply Bechner inequalities directly or to apply our equivalence between modified Luxiable inequality and Bechner inequality, and then apply the moment bounds. And so the hard work on proving the functional inequalities was done earlier by various authors. So we have something for Cauchy type measures of these viable type distributions. We have inequalities for symmetric groups or for stochastic covering properties. Let me perhaps say something in the last minutes about the Glauber dynamics. And if I have enough time, maybe just a few sentences about the Poisson space. So what is the Glauber dynamics? We have, it is also called heat bath or Gibbs sampler, especially in the Monte Carlo, Markov chain Monte Carlo community. We have a product set, a finite product. And now by mu I, we have some probability measure and some vector x with law mu. And for I, by mu I, we denote the conditional distribution of the ith coordinate given the remaining ones. So we think of it as the regular conditional distribution. And the Glauber dynamics says this type of generator, maybe let's say it in words. After an exponential time, so each coordinate has its clock. The clocks are independent, and when the clock ticks, we look at this coordinate, we look at the other coordinates and replace the coordinate that was chosen, the one at which the clock rank, we replace it by its conditionally independent copy, conditionally given the remaining coordinates. Right? And one can show that then this Markov process converges. I mean, the mu is the equilibrium measure. And for example, here I speak about the continuous time because we are in the setting of Dirichlet forms, but in the discrete time, this is often used in Monte Carlo methods to sample from mu. And our inequality in this setting is that if this Glauber dynamic satisfies the modified Luxiable inequality, then we have the following estimate. And it turns out that up to constants, when you, in fact, what Boucheron-Bousquet-Lugosi-Massart proved was this Bechner or modified Luxiable inequality for they didn't call it that because they had a product measure, but it can be interpreted that it was the inequality for the Glauber dynamics and the product measure, right? For the product measure, replacing by an independent copy is the same as what we have here, right? So here this xi is obtained by replacing the ith coordinate by an independent, conditionally independent copy of xi given, conditionally independent given the remaining coordinates. And now one can, what can one get from this? For example, if we have a measure on a cube, which satisfies this Luxiable inequality, I should mention here, it should be written for the Glauber dynamics, then we have those inequalities for polynomials that we had before, right? The same as in the Gaussian case, the same as under the Luxiable inequality, but we have to assume, this is just for a special class of polynomials, we have to assume that they are tetrahedral, so we assume that they are affine in each variable. They, none of the variables appears in powers higher than 1. So in some applications, it's not a restriction because, for example, if these are polynomials which appear in combinatorics and the arguments take values only in this set, -1, 0, 1, then of course, every polynomial can be written in a tetrahedral form because of higher powers reduced to power 1, right, or -1. So we get such an inequality. And the reason for this assumption that it is tetrahedral, this is from the fact that we have to relate this discrete gradient from the Glauber dynamics to the usual gradient of the polynomial, and then we can repeat the proof that you saw. And I don't know how much time do I have. I think I have already exceeded the time. So
if you need a couple of minutes, it's fine.
Okay, so let me just show you examples because I realized that it was all very abstract and dry for the moment. So usually for this Glauber dynamics, this Luxiable inequality or mixing is proved with some Dobrushin type conditions. So you construct a matrix which tells you how conditional distributions or certain coordinates depend on changing some other coordinates. And then you look at the norms of such matrices. You need also some assumptions on the smallest possible atom in a finite case, and then you can prove the modified Luxiable inequality. It was done first by Marton, and then Goetze Sambalens Sinulis. So Marton proved worked for mu having full support. They generalized it, but I speak here only about this full support for simplicity. And now I can, what I want to say is that there is a criterion, and some authors, especially Sambalens and Sinulis, worked out examples which allow us to verify our assumptions, and because of that to find moment estimates. So for example, for the Ising model, which, well, as everyone knows, describes the spins or some social interactions, we will look at finite graphs, and the Ising model is given by such a measure here. So we have interactions described by a quadratic form and some external fields described by a linear form. So then this condition translate into such assumptions, Dobrushin type assumptions on this matrix and vector of coefficients, and we get inequalities for polynomials. So this gives applications to, some of those inequalities have applications to testing Ising models, but I'm not an expert on this. I just know that they have been applied. Then there are exponential random graphs, which are graphs in which the energy is depends on the number of copies of some fixed graphs in your random graph. So if you look only at the number of edges, it corresponds to the classical Erdős-Rényi random graph. In general, you can look, for example, punish or reward for the number of triangles in the graph. So the edges are not independent anymore. And also Sambalens and Sinulis found a sufficient condition for this Luxiable inequalities, which when translated into our setting can be used to get those bounds for polynomials. And from this one can, for example, get bounds on the number of triangles is in such an exponential random graph. So I don't have time to analyze it. This is just some inequality which let me just say that it resembles the inequality which is known and in some ranges of parameters optimal in the Erdős-Rényi case. It resembles, but it's not exactly this inequality, so there is some work be done here. And just very briefly, I would like to mention the Poisson process because I know that many of you work with Poisson processes. So concentration for Poisson processes was extensively studied, for example, by Bachmann, Pecati, Reitzner recently. There are also transportation inequalities by Goslan and Eri. And here, so this is the case where we have the space is not discrete, it's not finite. The modified log Sobolev inequality holds, and the usual log Sobolev inequality does not hold. So the Dirichlet form is written in terms of this add-one operator, right? So eta is interpreted, the Poisson point process is interpreted as a counting measure. And we look how the value of the function changes if we add a point at x, so we add Dirac's delta, or if we remove a point from the Poisson process. And using some Mekes formulas, you can interpret this Dirichlet form in terms of the Carré-Duchamp operator. Wu proved the modified log Sobolev inequality, and in terms of such expressions, you get moment estimates. So modified log Sobolev inequalities were used earlier. Oh, I should mention that this was recently recovered by Sambale-Sinulis and Tele, roughly speaking, independently from us. We were a little bit faster in putting the paper on archive, but well, it is really within 1 month, so it was independent. And we have some applications, for example, to suprema of Poisson stochastic integrals, to Poissonian statistics in a geometric context. But, well, we are not very satisfied with those applications. Well, we are not experts on Poisson processes and stochastic geometry. We are not satisfied because those applications that we have in most situations can be recovered due to certain special properties of those functions. They can be recovered by earlier approaches using directly the modified log Sobolev inequality. So what we would like to have is to have a natural geometric example in which the tails are heavier, and the usual approach with modified log Sobolev inequality, the Herbst approach, does not work. I know that there are examples of some geometric functionals which exhibit heavy tails, but I don't know if this moment inequalities can be applied to them. I think, well, I would be, of course, very happy to see such applications. Okay, so sorry for making it longer. Thank you very much.
Okay, thank you. So are there any questions, comments?
Okay, I have one, Radek. So when you mentioned that the condition in the Ising model or the Glauber dynamics is similar to Dobrushin uniqueness, is it exactly the same? That you need that the alpha is positive and beta is positive? Is that exactly Dobrushin's, or there's some difference?
It is Dobrushin here. Okay, because here, you know, here you have this maximum of coefficients. It's a question of what you call Dobrushin, because here I mean this condition, which I have here, implies this condition. But what I want to say is that, so this is quite often called the Dobrushin condition for the Ising model, but this is the condition on the matrix of coefficients, right? And this is what I called earlier the Dobrushin condition was the condition on this matrix, right? And here I have the operator norm of the matrix, and here I have some other norm of the matrix, right? And this is the only difference. So that's why I didn't call it. I didn't say that it is the same condition, but
okay, thanks.
They derive from this one, the previous one.
Okay, thanks.
In this
Okay,
this triangle counts, what is the result? Can you just show that again? I mean,
yes. So if you look at the number of triangles minus the expectation, then it is well, this it has three regimes, and it is because this exponential random graph is invariant, is exchangeable in some sense. It's invariant under relabeling. So you can speak about, when you fix some two vertices, you can speak about the probability of finding an edge there, and the probability of finding a cherry like that, right? And these are our A and B. Yes. And K is the constant coming from this result by Sambala and Sinulis. And here, okay, here there is a problem. So maybe let me explain it like that. We proved a similar inequality because the story is very long in the independent case. And a breakthrough, like they were proving better and better inequalities for such subgraph counts. First, Jansson, Ruciński, and Oleszkiewicz proved an inequality which was essentially optimal if the probability of an edge was separated from 0. But it missed some logarithmic factors if P was converging to 0. And then Chatterjee was able to introduce those logarithmic factors for triangles, DeMarco and Kahn for cliques, and we were able in certain range. So for P going to 0 but not too quickly, we were able to do it for cycles using exactly those inequalities for polynomials with those partition norms, so that I presented before in the independent setting. So it is one of those rare examples where you can really evaluate those norms by some combinatorial methods. But then there was another breakthrough by Chatterjee and Dembo, and they allowed to they connected it with nonlinear large deviation, and Lubecki and Zhao and Chatterjee and Dembo, they connected the problem of finding the tail here to some optimization problem on graphons. But then in this classical here setting, people are interested, roughly speaking, in T equal to epsilon expectation of T, right? And then for triangles, this inequality, if P doesn't go to 0 too fast, or maybe the counterpart of this inequality we had with Pavel, gives the optimal result. Here we have two problems. We don't have those additional logarithmic factors, which were introduced there because the sub-Gaussian constants, when P went to 0, were getting better and better, whereas the Luxiable F constants do not improve. So this is one problem. The second problem, I think, is this behavior on gamma 1. So this corresponds roughly to the probability of finding P. And one can probably conjecture that in some of those inequalities, this dependence on gamma 1 should be improved or even eliminated at all. But I don't know how to do it. We just took the result by Sambala and Sinulis and plugged it into our estimates, right? Perhaps at some level you need to work harder for this specific problem than to use abstract results.
Nice. Thanks. Thank you.
Thank you.
Any other questions, comments? If not, maybe everyone can unmute themselves, and we can thank the speaker for this lecture.
Okay, so